Hello, we are Planeteer Environment and Infrastructure, the design team for the Montecito Desalination plant. To address emergency water conditions, the final design of this project has been completed with the purpose of constructing a desalination plant in order to supply the community of Montecito with a reliable source of potable water and complete the following objectives. 1. To improve water supply reliability for the community of Montecito. 2. To improve water quality for the community of Montecito. 3. To recharge depleted local groundwater tables that will serve as a long-term storage of potable water for Montecito and the city of Santa Barbara area. And 4. To design an intake system that has no impingement or entrainment and has an insignificant long-term effect on marine life. In order to complete the established objectives, Planeteer Environmental and Infrastructure has identified 4 critical work elements that will be the primary focus of this report. These elements include: number 1, a geotechnical report describing the soil characteristics of the project area, injection well, and off-site intake area. Number 2, a structural analysis report. Number 3, a water process design report, which includes a detailed description of the process that will be used by the desalination plant in order to recover potable water from seawater, and a series of drawings, plans, specifications, and diagrams. And number 4, a detailed environmental impact report per the CEQA, California Environmental Quality Act checklist guideline. Shown on your screen now is a section of our design build report that is a tentative outline of the costs associated with the construction of the project site, piping required for the conveyance of source water, product water, and our brine, water process components, and excavation gravel fill of the sub-ocean floor for the intake system. The costs associated with labor and material costs are summed in the excavation, tank construction, and trenching portions. The total cost, including our safety factor of 25%, has come to be a net total of approximately $29 million.
The purpose of the geotechnical report is to present the analysis for foundation design considering structural loads, soil conditions, predicted settlement, seismic events, and sea level rise. The on-site soil is characterized as soft, estuarine deposits of mostly silt. The first 5 feet of soil is sand deposits containing less than 5% fines, which might be a problem because it's susceptible to liquefaction. The plant is located in a high seismic zone. Using a seismic hazard map, the peak ground acceleration is 25.75 feet per second squared. In addition to seismic hazards, the UC Santa Cruz researchers estimate a sea level rise of 14 inches. A liquefaction analysis was done on the sand layer 5 feet below ground surface because it has less than 5% fines, making it susceptible to liquefaction. The calculated factor of safety indicates that the soil will liquefy. We recommend the first 5 feet of soil be excavated and replaced with fill material containing more than 5% fines. A one-dimensional analysis was done assuming a load of 3,000 psf. The total expected settlement is an average of 4.52 inches. Using Terzaghis bearing capacity equation for rectangular footings, the allowable bearing capacity of the soil using a mat foundation with the following dimensions is 8,148 psf after applying a safety factor of 3.5 to the ultimate bearing capacity. The mat foundation should have an embedment depth of 1 foot. The thickness will be 3 feet in order to counter the sea level rise of 14 inches and the expected settlement of 4.5 inches.
The main purpose and focus of the structural analysis report we assembled using MathCAD is the feasibility of the 3 sedimentation tanks on the site. Using the values described in the geotechnical report and the USGS website for seismic values, we were able to design the flat slab roof, columns, wall footing, seismic cables, and roof connections. We assumed a live superimposed roof load of 20 pounds per square foot and a uniform core wall thickness. The concrete strength we took into account is 4,500 pounds per square inch for the shotcrete and 4,000 pounds per square inch for the core wall, columns, flat slab, footings, and floor slab. We also used the specific weight of liquid, which is 62.4 pounds per cubic foot.
In conclusion, the sedimentation tanks needed for the plant are designed with a 54-foot finished floor elevation, an 11-foot liquid depth, and 97-foot inside diameter. The floor slab thickness is 6 inches, the roof thickness is 9 inches, the columns are 18 inches thick, the footing is 5 feet by 1.5 feet, and the wall is 10 inches thick, bringing the final outside diameter to 102 feet 10 inches.
The purpose of this report is to design a desalination plant that would convert 14 million gallons of seawater into 7 million gallons of potable water for the Montecito Water District, 30% of the product water being recharged into the Santa Barbara groundwater reservoir.
The desalination plant begins with a cutting-edge water intake technology referred to as an infiltration bed gallery. The infiltration gallery is a system of subsurface beds filled with porous gravel and sand media. The source water, which in this case comes from the Pacific Ocean, percolates through the voids in the filtration media and enters the intake pipe network. This percolation of water allows to take in large amounts of seawater without affecting the natural marine biota from the surrounding area. The infiltration gallery is at a depth of 18 feet below the sea floor, covering an area of 3 acres.
Upon entering the intake pipe network through the infiltration gallery, the seawater will be pumped by 3 CPT Sulzer pumps that are in continuous operation, with 1 backup pump for both maintenance and potential expansion. The water will be pumped through the pump house and enter the first stage of the desalination process.
The process begins with 2 1.15 million gallon sedimentation tanks with 1 standby tank available for maintenance and potential expansion. Chemical agents such as alum and ferric chloride are added to the influent seawater in order to remove particles through coagulation and flocculation. This process is crucial for ensuring proper function of the filtration devices that follow the sedimentation tanks because they protect them from falling and give them a longer lifespan.
The first filtration device used is microfiltration. Microfiltration is a process that removes contaminants from a fluid by passing it through a microporous membrane. The system will utilize 591 modules with a diameter of 20 centimeters and a length of 4 meters. The 591 modules will be arranged in a series of 12 racks. The microfiltration system precedes the reverse osmosis process because it, unlike the reverse osmosis process, can be cleaned through backwashing. This protects the reverse osmosis process from fouling and gives its membranes a longer lifespan. Because we have incorporated a microfiltration process before our reverse osmosis process, it is possible for us to increase our water yield from 50% to almost 80%.
The influent water enters the reverse osmosis process and is pressurized along a semi-permeable membrane and enters the exiting piping as pure water. 50% of the 14 million gallons per day of water fed into the system will be discharged as saline back into the Pacific Ocean. This stage is the most energy-intensive step of the treatment process because of the large amount of pressure needed to push the water through the microscopic pores in its membrane. Reverse osmosis uses the high-pressure gradient in order to separate dissolved solids and ions such as salts and minerals that are naturally found in seawater. Our system will utilize 480 modules arranged in 3 arrays with 32 vessels.
From here, 30% of the 7 million gallons, or 2.1 million gallons per day, will be pumped through pipes into the Santa Barbara groundwater basin, which is approximately 450 feet below the surface. The remaining 70%, or 4.9 million gallons per day of treated water, is sent to the chlorination process of fluorochlorine residual so that it can be distributed to the Montecito Water District. The water will be chlorinated using sodium hypochlorite and have a contact time of approximately 27 minutes before it is sent out for distribution.
The 7 million gallons per day of saltwater brine will be diverted back to the Pacific Ocean through a pipe that is located southeast of the desalination plant.
The purpose of this EIR is to assess and disclose potential impacts to the physical environment associated with construction and operation of the proposed project. The specific objectives related to the desalination plant and associated facilities and the land use applications through which they are processed include the following: to provide a local source of potable water to supplement imported water supplies available to the community of Montecito, to improve water supply reliability for the community of Montecito, to improve water quality for the community of Montecito and surrounding communities, and to locate and design a desalination plant in a manner that maximizes efficiency for construction and operation and minimizes environmental effects. Due to the time-sensitive nature of this project and the lack of sufficient tools and programs necessary to conduct a full-fledged environmental impact report, Planeteer Environment and Infrastructure was required to make several technical assumptions in order to facilitate a timely project completion. The following assumptions are: number 1, the combined total emissions of current ambient levels provided by the CARB 2012 South Coast Region Report with the impacts associated with construction and O&M activities were assumed to be less than significant. Number 2, the worst-case scenario in regards to impacts related to the discharging of brine waste was inspired by the Carlsbad Desalination Plant EIR and was assumed to have no significant impact. Number 3, the impacts to traffic and transportation with respect to project construction was assumed to yield no significant impacts, using an average daily trip addition of 100 trips to each affected street area. 100 was selected as a base and round number after comparing the number of average daily trips in the Carlsbad Desalination EIR, a 50 MGD plant, and scaling down the number for our project size. Number 4, The impacts to marine biota were assumed to be temporary and significant, but mitigated by timing construction with the seasonal changing of marine surface soil types, by choosing to construct during the time in which the affected area is predominantly gravelly, loose soil with little biomass. Number 5. The assumption has been made that the project would not require the additional allocation of resources to fire and police protection and/or public utilities such as power. And number 6. The assumption has been made that with all of the mitigation measures made to protect the tidewater goby, there would be no negative effects on the health of the species population. The environmental impact report for the Montecito Desalination Plant included a site visit and reconnaissance in order to verify the integrity of aerial photos, and an in-depth analysis of potential impacts and mitigation measures for 10 categories, which include aesthetics, air quality, terrestrial and marine biota, hydrology, soil and geologic resources, noise, hazardous waste and materials, land use and zoning, traffic and transportation, and public utilities. Among the 10 impact categories assessed by Planeteer, biological resources were the largest concern due to the level of impact associated with the construction of the infiltration gallery, as well as the project's proximity to an endangered species habitat zone for the tidewater goby, located in Mission Creek, due west of the project site. We had determined these impacts to be less than significant due to the short-term duration of construction and the zero impingement and entrainment of marine life during the operation of the plant. The discharge of our brine is directed east, away from the SB11 habitat zone. Thank you for taking the time to watch our video. We would also like to take this time to give our thanks to our technical advisors, Professors Tim Smith and Thomas Sink, and also to our course advisors, James Hoy and James Miller, for allowing us to work on this project. We are Planeteer Environmental and Infrastructure, and we'll see you at graduation. See you later.
Bye!